All right. So today is here we are, the 7th week. Only 3 more weeks to go. Wait, no, it's 8th week. Wait, 7th week or 8th week? 7th week. I'm sorry. 4 more weeks to go. Wow. I guess wishful thinking, but no, we got a fair amount to still cover. So it's good that we have extra time, but or normal amount of time. So what I want to do this morning is I want to go over the quiz. I'm almost done grading it, so I should be posting it soon. And we'll go over the quiz. I want to go over an example of a moment of inertia problem. And I also want to start talking about trusses. And we'll try to cram that all in this 50 minutes, and we'll see how efficient we are. But everything I'm covering here is covered in the lectures. But I'm hoping that this will give you kind of a preview so that when you do listen to the lectures, you'll be that much ahead. So, all right. Share screen. Okay, so here's our quiz. I want to show you. And so what I did actually with the quiz, and this is something that you can do with Excel. You can do it. Usually I recommend doing it by hand at first, but after you've done a few centroids, and I'm going to show you with the moment of inertia, you can actually set up an Excel spreadsheet to do your work. And so the trick with this problem, well, not the trick, but what I wanted you to see was that you have this piece of sheet metal, and it has a different density than the cylinder at the top. And the sheet itself, instead of worrying about the thickness, because if I had said that it's, say, 5 millimeters thick, then that would have made the problem more complicated, in the sense is that you couldn't have just said that areas 2 and 3 and 4 were had a X bar of 0, right? So you would have had to say, oh, they're 2.5 or half of that. So I didn't want to make that complication. So that's why I said assume it's essentially 0. And so I think the trick was, not the trick, I don't want to say it because I wasn't trying to trick you, but what I wanted you to get out of it was you had a linear or an areal density and you had a volume density. And but they work the same, is because when you're doing a problem where you have 2 different densities, it's really becomes it's a center of mass, but you need to account for that to make sure that you have the respective masses for each. So if we look over here, most of you did this that I've graded so far, you got the volumes correct, and or areas. And so for parts 1 through 4, it was an area. And then for the last part, it was a volume. I did see some unit conversion errors. For example, 1 centimeter or 1 millimeter squared is not 0.1 centimeter squared. It's 0.01. So remember, if every time you have a square or cube, you have to account for that in your unit conversion. So simple things like that can throw off the whole problem. Next was the mass. So what you would have done then is you've taken this area so for example, part 1, 150 square centimeters, and I converted these to centimeters because I gave you the densities in centimeters. And then you multiply it by that and you get the mass in grams. So here you have your mass in grams. This is ultimately what you want, because now everything's in grams. And so the fact that they have different densities is no longer an issue. Now you can just add everything up as you would normally. And then the rest is just like you've seen before. You have Y bar and Z bar. So you go ahead and you find them. Notice how with Y bar, I guess earlier I said X bar is 0 because X bar is 0 for everything. It's symmetrical. But Y bar is 0 for 3, 2, and 4 because it's right on the XZ plane. And then for 1, it's just half of that, 50. And then for the cylinder, it's just half of that, or 125. anyway, I think that's probably where the disconnect might have been is converting that. But again, this um, problem will come back on the final. So typically what we do on the final is we have a combined problem where we have the moment of inertia and the uh, center of mass in one particular problem together, which I'll show you. Anyway, so that's that. Any questions on it? Okay, good. So I'll post this answer just so you guys can see it, uh, and then go from there. All right. So moment of inertia. Now, by now you've watched the slides, so you're familiar with what moment of inertia is. And today you should have watched on Friday what the parallaxis theorem is. So you understand the parallaxis theorem. Are there any questions on the parallaxis theorem? That's good. So we completely understand it. No questions at all. All right. I like to hear that. So on this particular slide, so on this one, I'm going to go ahead and go to the document camera. Yeah. So this is the shape that we have. And I guess let me show you this first. So we're trying to figure out why it's so hard to focus. That's better. So we're trying to find the moment of inertia. So you have this shape. And so there's different ways you could approach this, but I think the easiest way on something like this is to find the moment of inertia of the rectangle, the 8 by 5 inch rectangle, and then subtract off the moment of inertia of these open spaces, which are just 3 triangles. So you have I -2, -3, -4. And that's how I would approach problems like this. And so, of course, the first thing you have to do with this problem is you have to find the centroid. So you have to find the centroid. And then once you find the centroid, you have to then use parallaxis theorem to find the individual d values. So remember, the d values are the distances from the centroid of each part to the global centroid. So if we look at this, I just want to show this because here, what I've done schematically is I've shown you here, I've already found the centroids. So the centroid for this whole object is x bar is 3.69, y bar is 2.15. So that puts that at about, there's the center of mass, area, volume, gravity, whatever, and that's there. So when you're doing the parallaxis theorem, of course, we know that we want to take each piece. So for example, if we had this triangle, we would say, okay, what's the moment of inertia of a triangle? Well, about its centroid, it's 1/36 BH cubed. So, and that of course depends on the orientation. So if we're trying to find IX, right? So if we're trying to find, IX, and so you see IX in the book, it's usually over it. That means not without this, with the X, but over the big I. That's about the centroid. So you have 2 different ways of finding moment inertia. You could find, I could specify an axis. I could say about, say, the x-axis, or I could specify x prime, and I could put an axis anywhere. Or you could say about the centroid. That's the most common type of problem we do. So once you have the centroid, then you know it's IX. But in order to find, like say, let's just look at this triangle. We say IX of, and that's of 4, right? Section 4. That's going to equal IX of its about its centroid plus AD squared, right? That's the parallel axis theorem, because since the axis that we're interested in is not the centroid of the object, we have to use this distance in order to figure that. So what we do then is we just replace this with 1 over 36 BH cubed, right? Where we know that the base in this case is 8 and the height is 2 based on our drawing. And I'm going to show you an example with more. I'll show you the same problem with all the numbers in it, but I'm just using this one particular one just to show you. So you have this part here, and that's saying if you just had your triangle like this, and you just wanted to know what it was about that axis, what's Ix right there about the centroid. So that would be this 136 BH cubed. And then we have to add to it AD squared. So of course the area is 1/2 base times height, that's the area, and then D squared. So D again is this distance. It's the distance from the centroid of this object. Since it's 2 inches tall, then its centroid is 1/3 of that, or 0.6666. And then its distance is the difference between that and that, or 2.15 minus 0.67. And then that's squared. So it's not AD all squared, it's just D squared times A. So you go ahead and you get that number. And then of course, because that's an empty space, this final answer is a negative. And that's the thing that's important when you're doing these parallel axis theorems, is treat them as all positive, meaning that they exist. Don't put any negatives in here until the end, and then subtract off the entire value from the actual object. Okay, does that make sense? Any questions on that so far? Good. So you could do the same thing if you're doing IY, in which case your D distances would go this way, right? It'd be just, if it's easier to visualize, you just flip it. So if you're doing IY, then now your distance is just, if this is the center of this piece here, this triangle here, then it's just from there to there. And that's it. So these aren't really super difficult. Just the important thing to remember is, and this goes to your homework too, is that you always have to go to the centroid. And I think that's something that can sometimes be forgotten. So for example, there's a homework problem that you guys have that looks kind of like this, right? So in that homework problem, you have to first find this here. So you're finding y bar, right, for the whole thing. And then wherever that is, you're going to find Ix about that centroid. So now you can't just draw a line here and go from here down and call that your D for, let's say this is part 2, this is part 1. That doesn't work because that's not the centroid. So what you have to do is you have to go from the center down. That's the only correct way to do it. The thing is that you don't have this equation. Now you could look it up, but it's actually quite easy to derive. And I do that, I believe, in my lecture. But just think about this. If you have, remember that Ix equals Ix bar plus AD squared. So you know you can find Ix, this value here, right? That's in your book. So you can then deduce Ix bar, which is what you're looking for, equals Ix minus AD squared, just by moving it to the other side. And now you have this, which is pi over 8 r to the 4th minus AD squared. Well, what's D going to be? Well, D is going to be this distance here, right? Well, we know that that distance is 4r over 3 pi, right? Because that's the centroid of a half circle. So you can plug that in, expand it, subtract, and you'll end up with Ix equals some constant times r to the 4. And that's what you have to use to solve this. And that's what you're going to have to use in any problem that you have that has a half circle or semicircle, which will most likely appear on a quiz or the final. Okay. All right, so that's that. Let's go back to this problem here. So we're back here. So we have our spots. I've kind of showed you what we want to do. So here's I got the centroid again. I used a Excel. So I have my areas, plug in my X bars, plug in my Y bars, and then you can set Excel to do all this by itself. Get your sums, and there you got that. So pretty easy to do. And if you're doing a lot of these problems, it's, you know, it's definitely a benefit to having to do them all longhand. Sorry. Okay, so here we have, this is how I did the moment of inertia for this. And so we have Ix. Now all this is here is just the 136 BH cubed. So I went through. So for example, part 1 is just simply one big rectangle. So it's just 112 BH cubed. And then you just change the base and the height depending on the orientation. And then the rest of these Ix's, they're all going to be negative. And so what I do is I go ahead and I put that in, and actually, let me see. I'm going to share there we go. Let's share this instead. And then you can actually, you guys can see my Excel sheet now, correct? Yes, no?
We only see your paper.
Oh, you only see the paper. Have you only been seeing my paper this whole time?
No, we saw your PowerPoint, but we don't see your Excel right now.
Oh, I'm sorry about that. Okay, well, thank you for saying it. Let me try to get that fixed. Go back to this. What's going on here? No, that's not right. Oh, I see what I gotta do. There we go. Now you should see it. You guys seeing it now?
Yeah.
Okay, good. Thank you. Okay, so this is a little easier because now I can show the equations. But so when you go up in here to I just put in the 112 BH cubed, as you can see here. I just 136 BH cubed and so forth. And then do the same thing for IY, so you get your equations. And then area. Area I found was just easier just to put in the actual number, but you could also have it somewhere else if you wanted to. Then you have D, and that's the distance I talked about, the distance between the centroid of the entire object to the centroid of the individual piece that you're looking at. And then, so I found the D's, and again, I'm doing it for IX and IY. So these D's, the thing that can sometimes be confusing is that's why I put the IX in parentheses, is this D here represents Y bar of the global object minus Y bar of the individual object. Because remember, when you're doing it about the X-axis, the Y bar is what you're interested in. And then for the distance for the IY, it's the opposite. Now we're looking at the X bar of the entire object minus the X bar of the individual object. And then here, just a matter of taking the area and this squaring it. And then the nice thing is that because it's all added together, you can just simply add up all these terms, and you can add up all these terms. And so essentially your answer, so for IX is just 64.67 plus this 80 squared. And so and so then once you get your answer, you notice 17.58. So And then you do the same thing here. You have 170 minus 100 added to a negative 126, you get 44.02. So important thing is if you get a negative moment of inertia, then you've made a mistake, because that's impossible. So you can't have an overall negative moment of inertia for your total. So just if you do choose to try it this way with Excel, then just be careful when you do your numbers. But anyway, any questions on that? If you want to try this for your homework, instead of doing it longhand, that's fine. Just what I would, when you turn it in, just cut and paste this sheet. So like I did, I just basically copied this into Excel, and that's fine. You don't have to send me the Excel spreadsheet. So it's your option. Okay. All right. Okay, let's talk about trusses now. Now, trusses, that's something they're conceptually, I don't think they're not really something that's abstract. That's the thing I like about this class is, unlike some of the classes you have, a lot of the stuff we do in here is not abstract. It's, you can understand it, and they're things you see every day in the real world. So what we have in this this first example is, if you look at a truss for, say, a bridge, or you notice that it basically consists of a lattice of two force members. And so the thing is, when you're analyzing a truss, the nice thing is that they're either going to be in tension or compression. And so, and you always know the direction of the force, because the direction of the individual member. The member can't hold any kind of a lateral force. It can only hold a force in its direction. And that's, I mean, it can, but compared to the force it can hold in the direction in either compression or tension is much, much greater than what it can hold in another direction. That's why we just look at it as all two force members. So here we have commonly used bridge trusses. These are just different designs of them. And the interesting thing is that, I'll come back to this, but there are members that don't carry a force, and we'll talk about that. They're called zero force members, and that's something. So for this week, the lecture is going to cover basic trusses. That's Wednesday's lecture, and then Friday is method of sections and zero force members. So, but once you understand these basic of trusses, then you should be able to solve them, the problem. So here we have, if we look at an individual member, P is tension or is in compression. And so a way to think about that is, if you were to put like a pencil between your hands. All right, so imagine you take a pencil and you put it in between your hands. Now, if you push in on your hands, you'll notice that, what's the pencil doing? It's pushing into your skin. So like the pointy side, you can feel it pushing in your skin. The eraser side, you can feel it pushing into your skin. And so that would be, you'd be putting it in a sense of compression, right? So you're compressing the member. So that's why in compression, the arrows both point inward. And so this is something that's important to understand, this, because when you're doing these analysis, you have to differentiate between compression and tension in order to get the right values. If you were to glue your pencil to your skin and then try to pull your hands apart, you would feel that the glue would pull away from the skin, and that would be the tension. And so the arrows would then point away from the pencil on both ends instead of towards. So that's the difference between the two. And the thing is, you don't have to know ahead of time when you're doing your calculation whether it's in tension or compression. You just have to do the calculation, and if you're right or wrong, it'll tell you by a negative sign. Now, if you have a point that you're dealing with that only has 3 vectors, then you can set up a force triangle And then using the ratio of that triangle, you can determine the ratio of those forces. So for example, in number 1 here, you have what would typically be a corner of a truss, where you have the reaction between the ground and the truss, and then you have a downward member and a horizontal member. And so in that situation, you can put them together like they show you as a triangle, and then you can just solve based on ratios. And generally, when you're doing trusses, when we start out, we always start in a corner where we only have 2 unknowns, and then we work our way up through the truss. Because if we start farther up, then you will have more unknowns than we can do. So for example, if you look at joint B, if we were to start there, we have 1, 2, 3, 4, 5 unknowns. So we may not be able, we may know 2 of them, but if we have 3 unknowns, we can't solve, because when we're in 2 dimensions, we only have the 2 equations to start with: sum of forces in the x, sum of forces in the y. Okay, so this is an example I want to talk about, and this was on the sheet that I sent you guys last night. Let me go ahead. So here we have, and one thing I want to point out on this is that you'll notice that this side here is mounted on some kind of a fixture where it can support a load in the x direction and the y direction. Whereas on the other end, you notice that those are wheels. So when you see something like that, it means that this end is free to roll back and forth. So it has no x reaction. So by inspection, if you look at this entire truss, you can see that because there's only 2 vertical forces and no horizontal forces, then you can surmise that AX is 0. But when you initially draw your free body diagram for it, you want to put in AX and AY, because it potentially could support a load. It's just in this loading configuration, there is none. So how do we start a truss like this if we want to solve it? Well, like I said before, is we want to start in the lower corner, okay? So we start over here and we work our way through it. Now, how do we do that? So I'm going to go ahead and transfer to my sheet. There we go. So there's our truss. So we have 8,000 pounds, 3,000 pounds. We have our reaction AX, AY, we have reaction EY. Our distances are 6 feet each horizontal member, and 8 up. So that makes us a nice 3, 4, 5 triangle. That's what that does. So that'll work well. So first thing we need to do is we need to figure out what is AY and what is EY. Now we won't solve the whole truss, but we could start in this corner and we could work our way through and solve for every member. But once we do a few, we don't need to. And so so normally in a homework problem, I would say solve for members and all this, maybe 3 or 4. That's it. After you do a few practice problems, you'll get the hang of it. So I don't believe in giving you hundreds of trusses to work on. It's kind of like learning to multiply 3 and 4 digit numbers. You don't need to do 100 of them to know how to do it without a calculator. Okay, so we start off with summing the moments. So the first thing we do is we pick a point, we sum the moments. So if I sum the moment about A to 0, then what I'm doing is I'm just saying I have 8,000 times 6. So in this case, what I'm doing is I'm saying that clockwise is positive. So I'm changing the convention just for this. So 8,000 times 6 plus 3,000 times 12. And then that's going to be minus EY times 24 equals 0. Okay? So all I did was I took this force times this distance, that force times the distance, and then all that's balanced by this. So I solve, I get EY equal to 3,500. So I know that EY plus AY have to equal 11,000, right? Because this and this have to equal the total up here. And so therefore I can deduce that from this, I do the complex math and AY is 7,500. So we need that to start, okay? All right, so now, as I said, the first thing we're gonna do is we're gonna start in a corner. So we're gonna go over here. Now, we've seen by inspection that AX is 0, okay? So we know AX is 0, so we don't have to worry about that. So let's start with joint A, all right? Now, if we look at joint A, what do we have? Well, if we look at it, we have here's our joint. We have this coming up. We know that's 7,500 pounds. And then we have these two. And so what is that? It's AH and AB. So we have AB and AH. All right. Now, if we make them into a triangle, then we can draw them just like this. We know that this is going to be a 7,500. And we know that this is going to be the AB. And then this is going to be the AH. Now, notice that if we look back at here, we know that all of we only care about joint A. All the other joints in the truss don't matter because we know that each joint has to be in equilibrium in and of itself. So if we look at this, these are the only things that matter at this point, the only forces. Now, if we know that we have 7,500 pounds going up, then since this has no vertical component, then we know this has to go down, doesn't it? Because that's the only way it's going to counteract this 7,500, so it's in equilibrium. And if that's going down, that means its X component's going to the left. This has to go to the right. So notice how that's how this is drawn too. This goes to the right, that goes down. So AB, we can see right away, is in compression. And AH is in tension. Because AB, if it points towards the joint, it's in compression. Away from the joint, it's in tension. So now if we want to calculate these respective values, we look at our triangle. Well, we know that's a 3, 4, 5 triangle. So we know that this is the 3 side, this is the 4 side, and this is the 5 side. So then what we can do is we can say 7,500 is to 4, as AH is to 3, as AB is to 5. So then it's just a matter of multiplying. So you have that times 3 gives you that, or that times 5 gives you AB. So if we do that, we get AH equals 5,625 pounds, and we know it's in tension. And AB is 9,375 pounds, and that's in compression. So far, so good. So this is similar to what I'll be talking about in my lecture, but in my recorded lectures. But hopefully, you can see this as something that's a process that'll be consistent throughout the trusses that you'll look at. Now, the only difference I find is the geometry. And so this is a very straightforward geometry, but sometimes the angles aren't as nice. They're not nice 3, 4, 5 triangles. And that's where it can become a little more cumbersome. So at this point, then you have to decide, well, what are you going to do next? You always, like I said, you always start in the corner and then you gradually move your way through the truss. Now, at this point, we could go to here, or we could go up to here. Now, if we go down to H, then we know 1, 2, 3 unknowns. So that's not going to work too good because we don't know it. But if we go up to here to B, we have 1, 2 unknowns. So let's go up to B, and then we can solve for this and this, and then we can come down here. We'll know this one, then we'll just have the 2 unknowns. All right. So if we go to joint B, so joint B. Now let's just draw it. So here's joint B. We know that we have, here's AB. Now we know it's in compression, so it's pointing towards the joint on both ends. And then we have, here's BH. And then we have BC. And then we also have this load of 8 kips. Okay. Sorry. So you have 8 kips, you have AB, you have BC and BH. Now we don't know which direction BC and BH are, so we can guess. Now AB is going up, and I don't believe the vertical component AB is bigger than 8. So, and since BC has no vertical component, I believe BH is going to have to go up 2 in order to balance that. And then with BC, because this is pointing towards that direction and these are both vertical, BC is going to have to point that direction in order to counteract that. Okay. So you can deduce some of this just by looking at it. But if you're wrong, again, you'll just come up, if, for example, up here, well, this isn't a good example because of the triangle, but if I come up with a negative, then I know that I guessed the wrong direction. So now with this, then I just use my 2 equations because I'm not, you could make, I guess in theory, you could make a 4 polygon and do it, but I've never tried it that way. It seems like it'd be a lot more difficult, but more power to you if you want. So I start off with, I sum the forces in the y direction because I have my two unknowns and my 2 equations. So if I sum the forces in the y, I know that the y, since this is a 3, 4, 5 triangle, I know that 4/5 of AB is going up, and I know I'm going to add that to BH, and then I'm going to subtract the 8,000, and that's going to be equal to 0. Now, if I substitute in 9375, so 4/5 times 9375 plus BH equals 8,000 equals 0. I'm sorry, equals 8,000. Then I find that BH equals 500. All right. So 4/5 of 9375 is 7,500. So that gives me 500 residual. So that's that. So BH is 500 pounds in compression. And you'll notice at the bottom of the sheet I sent you, there's a table. And that's typically how we usually fill them out. We say you have compression or tension, you have the magnitude in the load, and then you have the individual member. So that's that. So you have BH. So then we can go ahead and sum the forces in the X to 0. And if we do that, well, then in that case, we just have what? We have 3/5 of AB minus BC equals 0. And so in that case, then we have 3/5 of 9375 equals BC, or BC equals 5625 pounds in compression. Any questions so far? Make sense?
Professor, at joint A,
Yeah.
you said B or AH is in tension. So that means at point H, that would be compression if you're looking at it from the A perspective.
No, it's still in tension. Has to be.
So when one segment's in compression or tension, it's like that for any point it touches.
So think of it as like the pencil, right? If I have a pencil and I push on it, right? If I push in, what do you feel? You feel the pencil pushing out like that, right? So you're compressing the pencil. So if you look at it's just like in the drawing you have, if it's in compression, then this is tension, that's compression. It's always pointing in. So if we go back to this, then in our truss, then if that's compression there. If that's tension, that's tension there. Okay. So that is something that I get a lot of questions on. Why is it? How can it be? But if you think about it, if these ends aren't both pointing away from each other and they're both pointing the same direction, then they'd be moving, wouldn't they? So again, it comes down to, if you're compressing this thing on both ends, then what's this doing? So if you think about it, if I'm pushing down with my hands on that member like that, then that member, it's just the member. Now we're looking at the member, it's pushing into the joint on both sides, just like the pencil, as I squish it, it's pushing into my hands on both sides. All right.
Okay, got it.
Okay,
Thanks.
sure. Okay, so that's, now we've gotten to B, so we have time to go to H, and then you could see the pattern just repeats itself. So we could, if we were to go to joint H, then what do we have? Well, if we go back and we look at H, we have this, 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 and this. So we have HC. So let's go ahead and we'll draw it. We have, so we have this, and of course that's in tension. So it's like that. So it's my AH. And then I have HG. And then I have this here, and I have that. So here's my BH. Now we know it's in compression. And then we have HC. And we don't know which direction it's going in. All right. So let's assume that they're both in, let's assume that this is in tension and this is in compression. Actually, no, we don't want to do that because, well, I was going to do that just to show you how you get a negative. Now, intuitively, this should be in tension, shouldn't it? Because if this is in compression, then you have two joints coming down. So this should be in tension, but let's assume it's compression just for the sake of showing you the negative sign. So if we go ahead again and we sum the forces in the y direction to 0, then we essentially have minus BH and then minus 4/5 CH or HC, sorry, same thing, CH or HC. Now, where did I get the 4/5? Again, all of these triangles are 3, 4, 5. So you know that whenever you're dealing with an angle here, that this is the 4 side, that's the 3 side, that's the 5 side. So anything vertical is 4/5. So minus 4/5 HC equals 0. And so what we get is, now we know that BH, we know that BH was what? It was 500. So it's basically negative 4/5 of negative 5/4 of 500 equals HC. So notice how there's that negative sign there that we can't resolve because I guessed the wrong direction. And so what it would come out to be is it'd be HC in this case would be negative 600 625, which means I guessed the wrong direction. So it's actually in tension, not compression, which you could see obvious, but there'll be other problems where it won't be that obvious. So HC equals 625 pounds, and that's in tension. And then we sum the forces in the X, and obviously I'm kind of all over the paper just because I want to get this done, but it's try to be systematic in the way you do it when you're doing homework and you're not as rushed. But so what do we have? We have A8, we have negative AH because we know that AH goes to the left. So we have negative AH, and then we have plus HG, and then plus 3/5 of HC, and that'll equal 0. So then we just plug it in. We know it's negative 5625 plus HG plus 3/5 of 625. And then that'll equal 0. So it ends up that HG is 5250 in tension, a close cousin to 5150. So HG is 5250 pounds, and there we have it. All right. Any questions on that? We're almost out of time, but does that make sense? I'll take from your profound silence that it does. Okay, so the quiz will cover moment of inertia. All right, that's it. So it'll be a question on moment of inertia. And we will pick up next week in the next Monday's lecture. If I don't see you in office hours beforehand, we'll talk more. Next week we'll review method of sections, which is the next section of this, no pun intended, and then frames. So a lot of this is pretty self-explanatory. Go through lectures, come see me if you have questions, but otherwise I will see you guys in a week, or I'll see you in office hours. Thanks.
Thank you.
Thank you,
Thank you.
Professor.
Thank you.
Thank you.
Thank you.
Thank you.